Today we're going to talk about molecular orbitals, specifically sigma and pi orbitals. Molecular orbitals are useful in determining the behavior or movement of an electron within an atom. The first step in understanding this is by looking at the s and p orbitals. S orbitals are circular, so the electrons within this orbital move spherically. This orbital contains 2 electrons. There are 3 p orbitals. Each of these orbitals holds 2 electrons each, making it 8 electrons between them. Now that we know what these orbitals are individually, we can look at them together. A hybrid is something that can be combined from 2 different substances. 2 different but similar things are combined to make one new thing. Orbital hybridization is when 2 orbitals change their shape so they don't overlap 3-dimensionally. This new shape helps to create new orbitals. When an s orbital hybridizes with the 3 p orbitals, it is called an sp3 hybridization. This creates a tetrahedral shape. Because these are equivalent orbitals that repel each other with the same force, the bond angle is the same from the nucleus to any orbital. This is a bond angle of 109.5. Now that we know more about orbital hybridization, we can observe sigma and pi molecular orbitals. This is the symbol used for sigma. In this diagram, we can see that the 2 sp orbitals get close enough that they merge together to create a sigma molecular orbital. The most important part of this is that they come together in line with the nuclei. So here they come together to form one in the same plane as the nuclei here. This is the symbol used for pi. A pi molecular orbital is formed between unhybridized or unchanged p orbitals above and below the nuclei. You can see here that above and below the 2 nuclei, the orbitals have joined together. The most important piece on this diagram is that the top and bottom have joined together and the middle plane is untouched. Sigma and pi orbitals are bonding molecular orbitals, but there are also anti-bonding molecular orbitals. These orbitals have the same name as the others, but they are denoted by a star. So they are called sigma star and pi star orbitals. Like I mentioned, these are the anti-bonding molecular orbitals, so they do not form a bond with each other. They are orbitals that have an electron between the 2 nuclei of the atoms trying to form a bond. First, let's look at sigma star molecular orbitals. This little symbol here is what I meant about being denoted by a star. The sigma symbol is the same, but we know it is an anti-bonding orbital because of this little star. If you take a look at the sigma molecular orbital and compare it to the sigma star molecular orbital, you should quickly realize that they are pointing in the opposite directions. The electrons are pointing inward now and preventing the 2 from joining, whereas in this other diagram, the nuclei are pointing inwards. Because the nuclei are pointing inwards here, they can join. But because the electrons are pointing inwards here, they cannot join, which makes it this the anti-bonding orbital. Now let's take a look at the pi star molecular orbitals. You can see here that the pi symbol remains the same, but this time we have a star next to it, indicating that this is an anti-bonding orbital. If we compare the pi molecular orbital to the pi star molecular orbital, we can see that it is similar to the sigma and sigma star orbitals. Instead of forming those bonds above and below the nucleus, our orbitals have not joined together because they are not in the same plane anymore. The p orbitals above and below the nucleus are now different, so they cannot form a bond. If you take a look at the pi molecular orbitals, the 2 yellow orbitals and the 2 blue orbitals are on the same plane, so they can join. But in the pi star orbital, the yellow and the yellow are not on the same plane anymore, same with the blue. So now they cannot form a bond. Now that we know the differences between pi and sigma bonds and the different antibonding molecular orbitals, we can learn how to be able to tell which are which. The trick for determining whether an orbital is a pi, a sigma, or an antibonding molecular orbital is fairly simple. Let's look in this first box here. If we were to draw a dotted line down the middle of this plane, we would come into contact with the two nuclei. Referring back to our definitions earlier, sigma molecular orbitals merge in line with the nuclei. So let's draw our line down the middle plane. We can see that we have touched the two nuclei here. We can conclude now that this is a sigma molecular orbital, but is it just sigma, or is it a sigma star orbital? If it was a sigma star orbital, we would see the nuclei on opposite sides and the electrons pointing inwards. Therefore, we can definitively say that this is a sigma molecular orbital. Now let's take a look at the second box. If we were to draw a line down the middle of this plane, we would go through two unhybridized p orbitals above and below the nuclei. So let's draw our line now. Because of this, we can tell that this is a pi molecular orbital. So now, is it just pi, or is it a pi star orbital? If it was pi star, we could not have this line go through the two p orbitals. Because of this, we can conclude that the second box is a pi molecular orbital. Go ahead and try the last two boxes. Pause the video now to try them on your own. Here are the answers for the last two. This third box is a pi star antibonding orbital because when you draw the line down that middle plane, the line does not touch those two p orbitals. The fourth box is a sigma star antibonding orbital because our electrons are facing inwards, so our nuclei are not going to be able to bond together, making it a sigma star orbital. Thanks for watching my video on sigma and pi molecular orbitals. I hope this helped.